Good evening, everyone. Stand up and Dr. Dodson was telling us about his experience when he was in China. He gave a lecture in a monastery, and when he walked in, the monks all stood up and they clapped. And when he was finished, they all stood up and clapped as he walked out. So that's what we're laughing about. So my name's Sister Kathy Duffy, for those who don't know me, and I direct the Institute for Religion and Science here at Chestnut Hill College. And we're so happy to see so many students, as well as others, with us tonight. As many of you know, or maybe you don't, because I think for some of the students it's the first time here, the Institute is working to promote the constructive engagement of religion and spirituality with science and technology. So we would like to see, a nice dialogue going on here, even though some people think that science and religion are at war. So to do that, we have all these lectures, a reading circle, and we do some other things too, other events once in a while. If anyone is new here, other than the students, because you see the flyers around the college, but be sure to sign up for our mailing list so that you know what the next lectures are. So tonight it's a real pleasure to introduce our lecturer, my friend Bob Novak. Brother Robert Novak is professor of physics at Iona College in New Rochelle, New York. He joined the Christian Brothers in 1967 and holds degrees in physics from Iona College, Stevens Institute of Technology, and Columbia University. Since 1996, Bob has collaborated with the astrobiology group at NASA's Goddard Space Flight Center in Greenbelt, Maryland, a group that studies the composition of comets and the atmosphere of Mars using ground-based telescopes. As visiting astronomer at NASA's Infrared Telescope on the Big Island of Hawaii since 1997, he has visited the telescope over 20 times. This is a really, famous telescope. However, since then, he has remotely participated in observing runs at the NASA IRTF using the computers at Iona College. Now that we have technology, we don't need to go to the telescope. We can access it from a distance. So Bob was part of the team that identified methane in Mars' atmosphere and has authored or co-authored over 40 scientific publications. I've known Bob for many years. Bob, Dr. Peter Dodson and I participate together in Cosmos and Creation, a wonderful yearly weekend-long meeting at Loyola College in Baltimore, where we, along with other scientists and a few theologians that we let in, discuss ways that science and faith are not only compatible, but also that they can stimulate each other. So tonight, Bob will share some of his experiences and those of his students with this frontline research project, and one of the most important telescopes today. So please welcome my good friend, Brother Bob Novak.
Okay, thank you. Thank you very much, Sister Kathy. I hope you don't mind. I'll roam around a bit and explain a couple things that I'm going to show you. Over here, I've used this telescope. This is the one that the sister has been referring to. That's the NASA Infrared Telescope. And about a quarter mile away are the Keck telescopes. At the present time, each telescope is the second largest telescope in the world, has a diameter of about 10 meters altogether. The only larger one is in the Canary Islands, the only larger optical telescope. So I'll get through that with some future slides. But what happened during the 10 years ago or so, I had some nice grants from both NASA and the National Science Foundation. And part of these grants was a pretty large travel budget. And the reason was, if I got time on the telescopes, I wanted to bring students out to work on the telescopes. So this is a group of students that I went out with me. Overall, we had about 10 students going out to the telescope. And they all have done very well in their lives. These students went out in 2006, January of 2006. When we were making travel arrangements, I said that I'll pay for your travel to and from, and once you're at the telescope, I'll pay for your room and board. But if you want to spend a couple days down at the seacoast, you can. So a couple days became a week. And so that as they flew into Honolulu, they spent 10 days at one of the hotels in Waikiki, had a good time, and then finally flew over to the Big Island where I met them, and we went up to the telescope. Oh, let me go back to the students. What happened to these students? Well, she has a PhD in chemistry from University of Colorado. She has a JD in environmental law after getting a master's degree in environmental science from Duke University. She received a JD from St. John's University, and she became a doctor. She's working at the St. Jude's Cancer Research Center, and recently, after receiving an MD, she started a PhD program. So they certainly have turned out very well. I'm very pleased with them. So I'll give a little introduction to tell you a little bit about myself. And then I'll get into how we study the atmosphere of Mars by using these telescopes. I'll show you some of our scientific results. And at the very end, perhaps we could discuss this somewhat, how these scientific results have enriched my own spiritual life. Here's a little step-by-step biography of myself. So I grew up in Newark, New Jersey, and I attended the local parish school, followed by Essex Catholic High School. And there was a brothers' order, the Congregation of Christian Brothers were conducting the school, so after 3 years of high school, I joined the brothers in 1967. Part of our formation program was to do religious instruction, and also to major in an area that hopefully we could teach in. So during my novitiate year, I decided to go on in math. And I told the brother who was my academic advisor, I'd like to take this physics course. It sounds pretty interesting. Well, he put his pen down and he said, listen, how about if you major in physics and take math on the side? Well, that little 5-minute conversation made the difference in the rest of my life. And looking back, he had some pretty good insight, because I feel I'm much more suited to do physics than to go on in math. So I graduated from Iona College, majored in physics, and for the next 4 years I taught in various Catholic high schools, 2 different Catholic high schools. But meanwhile, I was going to school at night for a master's degree at Stevens Institute of Technology. When I finished that master's degree, the next thing I was sent up to Iona College to teach part-time, but also to get a doctorate at Columbia University. So I finished that in 1980, and ever since then, I've been a full-time faculty member at Iona College. So as I mentioned to some people already, generally I'm teaching. I teach general physics for the science majors. I teach electricity and magnetism for the physics majors. And I always like to teach a course for the arts and business majors. So currently I'm teaching astronomy. We meet Wednesday night. it's obvious that you have to meet at night because you can't do too much astronomy during the day. So I teach for 2 hours, and I try to set up telescopes, and we observe various things up in the heavens. The big thing this semester has been to look at Saturn. Unfortunately, Saturn is gone from the evening sky, but they want to see Jupiter and Mars. I said, great. Come back here at 4 o'clock in the morning, we'll set up the telescopes, and you can see some of the other planets. And since 1996, Iona received a grant from NASA that was followed by a series of other grants from both NASA and the National Science Foundation. So I've been pursuing a study with NASA since then. So these are various scientists at NASA that I work with in the Astrobiology Institute. Mike Muma has been at NASA for a while. He's in charge of the group. I also work with Dr. Karen Maggie Sauer, who's at Rowan University. She, like myself, are some of the university contacts that works with the group. And then these are various students who have been to the telescope. And you can see some students making believe that they're operating the telescope. Well, they are actually operating the telescope. And this is my colleague, Bancho Banev, and those are other students that have visited the telescope with myself. Well, we study the atmosphere of Mars. We also study comets, but I've been specializing in the atmosphere of Mars for the last 20 years. And to do that, we use ground-based telescopes. Now, as I mentioned before, and as Sister mentioned, between those 2 years, I had to make 18 trips to Hawaii. Some of them were with students to use the telescope, until somebody came up with the bright idea. Why do you go to the telescope to sit in front of a computer to operate the telescope? Why don't you operate the telescope by staying home and just tying into the internet? So I've had probably another 15 observation runs, but I either did that from my home campus, Iona College, or Yale University, which is about 40 miles away, depending which telescope we used. But I did get back to Hawaii this past January, and we had 3 nights on the telescope, but we were there for 12 nights altogether. So we did a couple other things, like attend the luau, go visit the volcano, little things like that. You know, we had a lot of downtime. What we use are infrared spectrographs. Now, I'll explain that a little bit more, what a spectrograph does. But in a night on the telescope, we take at least 400 images. Sometimes we take more, okay? Depending if everything is going well, we just keep on taking picture after picture after picture. And then the real work occurs when we analyze these images. So some of that takes months. I gave my first presentation on the data that I took in January a few weeks ago, and that was my summer activity, to put together that presentation. So I have to go back. We have a couple more days on the telescope in January, but I'll do it from right from Iona College, and we'll take more images, and hopefully we'll find something interesting. And so that we have presented our results both at conferences and in various publications. Now, the group I'm in, the American Astronomical Society, their conferences move around quite a bit. So a couple of weeks ago, the annual conference was in Provo, Utah. I've never been to Provo, Utah before. So it gave me an opportunity to move to Utah, go to Utah for a few days. But every 5th year, they have a conference in Europe. So that made me go to places like Paris and Rome and Cambridge. So it's not a bad organization to be in if you want to go to conferences. So we use data from 3 different telescopes. So this is the NASA infrared telescope. Okay, you've seen that already. Okay, it has a 3-meter diameter. By the way, the mirror weighs about 5 tons, and that's the smallest telescope. And this is the instrument that we did use for most of those 20 years. Next to that telescope are the Keck telescopes, and Keck 1, Keck 2. So Keck 2, we've been also using that. That's a 10-meter telescope. So you get considerably more light being focused into the instrument, which is located over here. And there are also some very large telescopes located in the Andes Mountains in Chile. Okay, this is one of them that we've been working with, and that's the instrument that we work down there. Now, the altitude over here is about 9,000 feet. The altitude for these telescopes is about 14,000 feet. Okay, so that these telescopes have an advantage because they are somewhat higher than the telescopes that exist in South America. You can see the clouds in the background. Okay, so this mountain, Mauna Kea, has about 300 good nights a year to observe. Anything over 250 is good. Okay, 300 nights is very good. So it's become a very popular place. The other thing about Mauna Kea, it's in the middle of the Pacific Ocean. So we don't get much air pollution, but it is a bit annoying to get there. Okay, it's a 15-hour flight between New York, one way or the other. Usually have to take about 3 different planes, but I get used to it. Okay, after all, we're going to Hawaii. Okay, it's much better than going to Provo, Utah. So we usually fly into Honolulu, and then we take another flight into the Big Island, and so that we either land at Hilo or over on the Kona coast on the other side. So the islands of Hawaii are formed by volcanoes, and the Big Island of Hawaii is formed by 5 volcanoes. Now, some of these volcanoes, 2 of these volcanoes are dormant, and one of the dormant volcanoes is Mauna Kea. It has not erupted in about 5,000 years, which is like the twinkle of an eye in terms of geological time. But again, 5,000 years, so I guess it's safe enough that you could build telescopes on top. Currently, there is an eruption that's taking place over here with the Kilauea volcano. It's erupting in 2 places. And the Mauna Loa volcano last erupted around 1984. There's another volcano over here that has not erupted in 200 years. And the joke in Hawaii is, when do you expect it to erupt again? Well, basically it erupts every 200 years, and the last time it erupted was 200 years ago. So you could fill in the blanks from there. And then there's another volcano, Loihi, that's located over here, that currently is under the ocean, but maybe in about 1,000 or 2,000 years it'll pop up out of the ocean and become another Hawaiian island. So we fly into Hilo, and you can see that Hilo is a tropical paradise, but off above Hilo on a clear day, by the way, there aren't too many clear days in Hilo, you can see the mountain so that it's about 40 miles away. You could just barely make out the telescopes on the mountain. When I was there in 2008, I got up in the middle of the night one morning. I had a couple extra days. I was staying near the seacoast, and I got up in the middle of the night. I didn't think anything of it, went back to bed. I turned on the news when I woke up, and I found out that the volcano had erupted. And this was in 2008. It's been erupting continuously since then. We made a trip there, a few days afterwards, and one of my colleagues took this picture of me. I got there a couple days before my colleague got there. I picked up my colleague on a Friday, and I said, tomorrow we're not going to hang out on the mountain. We're going to go down to see the volcano, because it's one of those sites that it's very rare to see an active volcano, and still from the point where it's relatively safe. Now, the volcano is up about 4,000 or 5,000 feet above the ocean, and when the lava comes out, it obviously goes downhill. Sometimes it goes towards a town. There was a case about 2 years ago where the lava flow was approaching a town and actually destroyed a couple buildings on the outskirts of the town. But you can see active lava going into the ocean, and the steam generated by it. So in one sense, okay, this is new land. Okay, we always assume that land is permanent. It's not. It comes and goes. So every year, about 50 acres are added onto the big island of Hawaii, and all this land is no more than 5 or 6 years old when I took that picture. Now, the telescopes are up near 14,000 feet above sea level. We live at 9,000 feet, and there's a little colony over here. These are dormitory buildings. This is a central building with offices, computers, a nice kitchen, a dining room, recreational space, and so on, because there are 11 research telescopes on top of the mountain. And basically, they're used every night of the year. So the people that work on them, visitors like myself, we have to get there 2 nights before we actually use the telescope to get acclimated to the altitude. And then we go up. It's about a half-hour drive from here up to the top of the mountain. There is also a visitor center where every night they set up some smaller telescopes that visitors can actually peer through them. And they have these camps here that are used by Boy Scout troops or, various other groups. The top of the mountain doesn't have any vegetation. It doesn't have any animals. They claim that there are insects up there, though I've never seen any insects. But you can see the remains of some of the volcanic eruptions over here. And the big thing with this mountain is that most of the time, the summit is going to be above the clouds. Okay, the top of the clouds is about 10,000 feet. So we're another 3,000, 4,000 feet above that. Okay, it makes it a convenient place to drive to, and also one in which you're above the clouds, again, 300 good days a year. The crater that's on top of the mountain, if we go around the crater, it's just littered with telescopes. So these telescopes over here are all optical infrared telescopes. Many of them are from other countries. The Subaru is the national telescope of Japan. It's not named after the car company. I thought they were the sponsor. But Subaru is Japanese for the Pleiades, the constellation Pleiades. And if you ever look at a Subaru, at the symbol on the car, you'll see the stars in the constellation, or an image of the stars in the constellation. So that's the Japanese constellation. I mentioned the Keck telescopes and the NASA telescope, Canada, France, Hawaii telescope. Gemini telescope is one of 2. There's another one in South America. There are about 13 countries that sponsor it. This is University of Hawaii telescope. There's another University of Hawaii telescope. If you take astronomy at the University of Hawaii in Hilo, you get an awful lot of telescope time. I guess that's an incentive for graduate students to go to the University of Hawaii. Okay, this is the United Kingdom infrared telescope. These telescopes here are more like radio telescopes. So the United Kingdom also has this telescope. Here's California Institute of Technology has their own telescope. And then this is a combination. It's a joint effort between Harvard University and the Smithsonian Institution. There's another telescope that you can't see from there. But this is a telescope that I use most of the time. A few times I've used a Keck 2 telescope, but I use the NASA infrared telescope pretty much every time I have gone to Hawaii, and I also use it remotely. So what we have over here, this is a picture I took. Okay, you can see the secondary mirror. And then I went inside the dome. Usually when I go there, we actually work inside the dome. And over here is the primary mirror. That's going to be 3 meters in diameter. It's highly polished, and it weighs about 5,000 tons. And all this other framework is going to be to support that. Okay, inside the telescope, there's a hole in the middle of the mirror that the light goes through. And on the rear of the telescope mirror, we have different types of instruments that take the pictures. So that this instrument over here is going to be what we call the National Science Foundation camera. It uses filters of different infrared colors to filter out different things. So with that, you can see weather patterns on the planets. You might be able to see some of the various surface formations. This is a spectrograph that can measure solids and liquids. And the instrument that I've used for most of my time has been Seashell, which is a high-resolution spectrometer that's able to detect gases. Now, I say most of the time because last November, actually about a year ago, this newer instrument was placed on the telescope, and the last time we went there, we actually used that instrument. The old instruments, well, we'll go into the size of these, but the old instrument, every image was about a quarter megabyte. The new instrument, every image is about 50 megabytes. So the new instrument gives you 200 times as much data. So far, my own experience of that is taking me 200 times the time to analyze the data. So I have an awful lot of work. In fact, the amount of data that I have in my pocket on this flash drive, that'll keep me busy for the rest of my life if I want to analyze all of it. Now, immediately adjacent to the telescope is the observing room, and this is David Griepe, who's the head telescope operator, and he's surrounded by instruments. All these guys, they're pretty funny guys. You can see the various statues that they have around. You don't see any pictures of astronomers or famous scientists, but you do see, these cartoon characters. Okay, that's where we sit. And this is the group that I went to the telescope with in January. This is Dr. Michael Buma. He's a longtime NASA scientist, very well respected throughout the world. This is Dr. Geronimo Villanueva. He is also a full-time NASA scientist. He's been working with the group for about 12 or 13 years. And this is Sarah Faggi. She's from Italy. She just received her PhD. This was one of the last things she did right before the PhD defense. She spent 2 weeks with us at the telescope. And she went back home to Italy and then came back to the Goddard Space Flight Center, where she is doing her postdoctoral work. So we study Mars. With any of these spectrographs, we use something known as a slit. So we take the image of Mars and we project it onto the slit. Now, this image of Mars is going to be a cartoon image, but we can place the slit, generally speaking, in the north-south direction, and in this case, we're at the center of the observable planet. Now, one of the things that we do is to move the image back and forth. So we get a series of different spectroscopic images, and so that we get, going back to math, they're going to be at different x values and different y values. So in terms of, say, an x and y type of projection, we can analyze the gases at each of those points. Now, we take a series of images. Okay, you can't see it too well in this image, but we are specifically looking for the gases, methane, and also water, H2O. So that when we take an image that's going to be at that particular setting, we get an image. We get an image that looks like that. Now, when we take an image, we're not just taking the image of Mars. We're taking the image of Mars through the atmosphere of the Earth. So we move the telescope a little bit and then take an image of the atmosphere of the Earth. Okay? Now, what we see in the atmosphere of the Earth is a lot of background, but we have methane located over here, and we have water located over there. So the position of the emissions is going to refer to the different gases. Different gases have different positions. So what we do is we subtract this minus that. Okay, then these are going to be chips that have thousands of pixels, so tens of thousands, maybe hundreds of thousands of pixels. So every pixel is going to act a little bit differently. So we do a calibration run over here. Okay, we expose this to a light bulb, and then we shut down everything. and we take another image of everything without any light shining on it. Now, the analogy that I want to draw is, suppose you want to weigh yourself. You step on the scale and you weigh 160 pounds. You step off the scale and the scale says 5 pounds. Are you 160 pounds, or are you 155 pounds? Okay, so we do a similar type of thing. We take this and we subtract it by that. We take this, and from that we subtract that. And then we calibrate every pixel because of the difference between the two. Now, this thing over here is a well-known scratch. When you get scratches on the chips, they don't disappear. They stay with it for the lifetime of the chip. So by having a nice clean image, and we have to do some other magic tricks to it, if we take an extract over here, we could say that's from the southern part of the planet, or we could take an extract over there. So by taking lines, this is a chip. It has a certain number of rows. By each row is going to refer to a different latitude position. And so that we graph it. And what we have graphed over here is, you could see over here there's an absorption of the Earth's atmosphere, there's another absorption, and there's another absorption. So these two would be water positions, that's methane position. Can't see anything in there. Well, let's move on. Now, the other telescope, the Keck 2 telescope, corresponding types of images look like this. And you can see that we get much more data, maybe about 4 megabytes altogether. And we get what was one line, we get several different orders over here. So by analyzing those, likewise, we could analyze the different gases. And they indicate some of the gases on this. Now, the new chip, the new instrument we have, each one is going to be 50 megabytes. So that's what one image looks like. Now, I spent my summertime analyzing these 3 lines over there. And I have to go back and analyze the other 37 lines that you see. So it's going to take me, that's what's going to take me the rest of my life. And not only did we have this setting, but we have about 4 or 5 other settings. So when you see me in about 10 years, maybe I'll be finished with all of this analysis. Now, let's talk about spectra a little bit. I'm sure you've seen something like this. We could say it's the rainbow effect. If you see a rainbow, light comes from the sun. It goes through a water droplet. Well, this is a prism. And then we see the components of the light that are located over there. So the white light that we see is really a combination of several different colors. And different types of atoms and molecules give off different colors. For instance, sodium light that we see all over the place on the streets is primarily yellow. Okay, mercury light that you see in fluorescent tubes is going to be a combination of various colors. Neon light that you see from these advertising tubes in front of stores has its own characteristic color. So the visible light that we see, we could measure it between here and here. Okay, so we have violet on one side and we have red on the other side. My friend Roy G. Biv goes right across there. So if we move to this side of the violet, that's what we call ultraviolet. If we move to that side of the red, that's the infrared. Okay, so we are looking at infrared light that is either going to be absorbed or emitted by the atmosphere of Mars. So the telescope and also the instrument is designed to detect the light that occurs over here. Then, of course, we have these other things like, X-rays and gamma rays. In order to see them through a telescope, they have to launch the telescope up above the atmosphere. Okay. Now, there are 2 different things, 2 different ways we could analyze the data. In one sense, we have absorption. So this is light going through hydrogen gas. And you see these different colors are going to be absorbed. On the other hand, if we put hydrogen gas into a tube, into a spectral tube, and shine it and analyze the light, we see the colors here and there. In other words, if we look at absorption spectra, we have a lack of light. If we look at emission spectra, we have the light being generated. By measuring the colors of light, or we call it by measuring the wavelengths of light, and seeing where the absorptions or the emissions are, we could identify what the atom or the molecule is. On the other hand, mercury looks totally different from that. So if we see these colors, we know it's going to be mercury and not hydrogen. Now, what we do is to target certain molecules. As reference, we use the atmosphere of the Earth. Okay, ozone is a pretty important molecule. There are different forms of water that we study, regular water and heavy water, and we're very interested in this ratio between heavy water and regular water. The common wisdom 30 years ago was that the ratio on Mars is 5.2 times the ratio on the Earth. We took more specific measurements and we found out, well, it's not as simple as all of that. Okay, there's a big variation there. We look at isotopic forms of carbon monoxide. It means we could have carbon-12, carbon-13. We could have oxygen-16, oxygen-17, oxygen-18. So we actually found 3 new forms, and also isotopic forms of carbon dioxide. Now, one of the things that we did is that we're trying to look for water and methane. And we found this group of absorptions, and somebody said, it's not in any catalog. So somebody said, it looks like carbon dioxide. We went to check, and sure enough, it was carbon dioxide. So that it was a distraction for us. But as being part of a distraction, we were able to publish 2 scientific papers in identifying these, up to then, unobserved forms, transitions of carbon dioxide. Now, we have found methane on Mars. Big question is, does methane come from life, or does it come from geology? If it comes from life, either active life or decaying life, we would expect to see ethane, propane, butane, and so on. Okay? If it comes from geology, we would see methane, but the ethane, propane, and butane would be much less than if it came from life. So we have a pretty good understanding of methane that comes from life, along with these other chemicals. We want to know what the origin of methane on Mars is. So if we could find any of these other chemicals, and those data are in my pocket, they haven't been analyzed yet, hopefully we can find out if the methane comes from something that was alive at one time, or if it comes from geology. Okay, it's a very subtle difference. This is a Hubble image of Mars. It's a pretty good image that we see. So what we do is we take our slit and we put it north-south on Mars. Sometimes we put it east-west on Mars. And we have different settings. Okay, this particular setting is going to analyze oxygen-2. And this oxygen-2 is going to be a byproduct of ozone. So that if we could measure oxygen-2 in its excited state, then we know it comes from ozone. And we measure ozone. So these dark regions over here, these are absorptions in the Earth's atmosphere. Immediately to the left of it, you see a bright band of color, a bright band. And that's going to be oxygen-2 from Mars. Okay, so the dark bands are oxygen-2 on the Earth. Now, when the light goes through the Earth's atmosphere, it's absorbed. When it comes from Mars's atmosphere, it emits light. Now, what we need is what we call a Doppler shift. So the fact that Mars is coming closer to the Earth when we took these data, you can see that the Martian oxygen is to the left of the Earth's oxygen. On the other hand, if Mars is receding from us, you can see these things, these bright bands move to the other side. It's like, I don't know if you have any big roads around here, but I tell my students, if you go down to Route 95 and stand on the bridge above Route 95, and you look at a truck that comes, you know that when the truck approaches you, you hear this high-pitched sound. And then when it passes you, the pitch goes down. Same thing happens between Mars and the Earth, okay? When Mars is approaching us, the light has a higher frequency. When Mars recedes from us, it has a lower frequency. So we need that difference in velocity in order to move the Martian lines out of the Earth's absorptions. So if I graph these at different times of the day, what I did over here was to put the slit east-west. Whoop, I showed you the end of this slide. You can see that there are different emissions at different local times. Local time is going to be the time on Mars, and if we put it together into a two-dimensional graph and make it nice, okay, you could see that for this particular time of the year, which is going to be late northern summer, late southern winter, most of the ozone is going to be in the southern regions. Very little of the ozone is going to be in the northern regions, and in the middle of the planet, there's not much ozone whatsoever. Okay, so here we took at a series, so these are one of the standard things that we do to get a seasonal development of ozone throughout the Martian year. So this refers to the end of winter in the northern hemisphere. This is the beginning of spring in the northern hemisphere. Notice that ozone is in the north polar region. There's some of it in the south polar region. This is mid-spring in the northern hemisphere. And we see the ozone going right across the planet. And then when we get to late spring, going towards summer, the ozone seems to collect in the southern hemisphere. Now, the other thing we study are going to be two different forms of water, regular water and heavy water. So these are the settings for regular water. These are the settings for the rover has been launched and is roaming around Mars at the present time. One of the things that they were looking for was methane. And you know what? They found it. So we found methane, they found methane. The fact that methane was found in two different ways by two different groups in different locations, all of our opposition disappeared overnight. So we were very happy about that. So these are the different molecules that we have detected. We have a lot of isotopic forms of molecules. We have a list of molecules that we'd like to do, okay? So we're going to do more spatial temporal variations. We're looking for other isotopic signatures. We want to find out if methane is from life or if it's from geology. One of the ways we could do it is to look at carbon-13 methane versus carbon-12 methane. There's a new system on many of the telescopes where one of the problems with anything you see through the atmosphere is that there are atmospheric effects. There are new sets of optics known as laser guide stars that can overcome some of the effects. And with the new instruments, especially this instrument on the NASA infrared telescope, they give us 50 megabytes of data versus 250 kilobytes of data. Okay, more data, more things we can look for. It'll keep me busy for the rest of my life, as I said. These are specifically the molecules we're looking for. Now, how does it affect my spiritual life? Okay, how does it affect the spiritual life of others? Well, being a scientist, I believe that I am studying God's creation. I'm getting a better understanding of God's creation. And in getting a better understanding of God's creation, perhaps we could get a better understanding of God. We were talking about this at our table, about a couple concepts, but I believe that if we get a better understanding of what the creation is, we can understand better our view towards God. Working on a science project, okay, we are part of a scientific community. Okay, a good scientific community would be a group of people that work together, they respect each other, they listen to each other. So, likewise, if we have a good religious community, we should be doing the same thing. Okay, the people that we go to church with. Okay, do we listen to them? Do we listen to their anxieties? I'm a member of a religious order. Okay, likewise within my local community and the larger community. Okay, if I could work well with the scientists, why can't I work well with the brothers I'm in community with? I like the parable of the talents in the New Testament. Okay, each of the individuals was given a certain amount of talents, and it wasn't the quantity of the talents that mattered, but what mattered was how the individual used those talents. So that the person that did not use those talents did not fare too well. Okay, so we are given certain talents, and I really believe that part of our spiritual insights or religious duties is to make sure that we do something with those talents. So that's another aspect. I said, for my own self, this is the way that I'm exercising the talents that God has given me. In science, we encourage others to do better. I remember my mentor constantly encouraging us to pursue the unknown. I remember sitting down with him one day, and I showed him the data that I was taking, and he said, well, you haven't told me about this or this or this. So by implication, he wanted me to figure out what this and that were. Unfortunately, I went back to him the next week and said, this is what this and this and this is. Okay, how'd you figure it out? I stumbled upon it, but eventually, when you meditate on these things, hopefully a solution can come about. Likewise, in the religious setting, okay, why can't we take our religious knowledge and try to get a better understanding of it? Why can't we take our spirituality and try to improve it? And encourage other people in doing it, okay, so that we could reap the benefits of ourselves and also other people. Science is an active process, so is faith. We develop our own insights in science, we should also develop our insights into faith. Okay? One of the things that we do from time to time, we used to meet on a Sunday morning, a group of those in our community, and basically, we almost facetiously called it the review of the week. But it was a review of those new things or those encounters that we had during the course of the week. And by understanding what other people were doing, say from a spiritual sense, it encouraged all of us to do better and to share our goals with each other and our insights. I like to say this, that many people have problems with the scientific view and the biblical view of creation. Okay. Now, when I started college, we took an awful lot of theology. I was becoming a brother. I was also, going through my regular studies. And we took 2 semesters of Old Testament. And of course, the first thing in the Old Testament is the book of Genesis. We spent a lot of time with Genesis. Okay, we analyzed it quite a bit. We didn't go much beyond that because I think the professor didn't know much beyond that, but anyway. But in analyzing Genesis, it appeared to us that the creation story was not the creation story of just the human writer of the Bible. It was the creation story that was the common creation story in the Middle East at that time. Okay, so that because the story, similar type of creation story, the days of creation, were in many of the other local cultures. Now, my view is that if somebody were to write the Bible today, the human start of the Bible would be the Big Bang Theory, because that is what we believe is the formation of the universe today. Okay, now, 50 years from now, that view could be different. 150 years ago, it could also be different. But I think from what we have learned, from what God has given us, the creation story within the Bible is not the same as our Big Bang Theory that we believe is the creation story according to science. The other thing I mentioned before, that I was at this workshop or discussion, and one of our colleagues, Brother Guy Consamagno, who's a Jesuit brother, he's also the director of the Vatican Observatory, gave a talk that I went to, that I attended, and the creation story came up as a part of it. And I mentioned that if the Bible were to be written today, we wouldn't talk about the days of creation. Rather, probably it would be the Big Bang Theory. And we have to distinguish between the human author of the Bible, the person that actually wrote the stories down on parchment, and the divine author of the Bible, of course, God. So that's very difficult. Okay, too many, well, a lot of people take it literally, but the creation story is an absolutely beautiful story, whether we go with the days of creation or this Big Bang Theory. Now, I just want to finish with a scenario for life on Mars. I'm giving another talk in 2 weeks, and it's going to be the astronomical search for aliens on Mars. So perhaps life existed on Mars billions of years ago. We know it had a thicker atmosphere. The atmosphere of Mars is very thin. There's not enough ozone to filter out the ultraviolet light, so that ultraviolet light goes right down to the surface. And if life were to exist, like the Martian, okay, if they're exposed to that ultraviolet light, not very good for him. It was a warmer climate, it was a thicker atmosphere, and there was liquid water on the surface. We believe that liquid water is needed for life. Now, there's a little story that goes along with this. Say life existed 2 billion years ago on Mars. And you always have the Earth being bombarded by asteroids and meteorites, more so then than now. And perhaps there was an impact, and so that debris went out into space. There have been meteorites found on the Earth that pretty much everybody agrees they originated on Mars. Now, suppose if some of this debris fell on the Earth, and inside of that debris, there were some of the building blocks of life, or maybe some part of life that was transported to the Earth. What are some of the consequences of that? This happened about 2 billion years ago. How long has life existed on the Earth? About 2 billion years, so. Well, anyway, let's take it from there, and we could continue it some other time.
So thanks a lot, Brother Bob. And what we usually do now is take a couple minutes at your table to come up with some good questions or comments. So I wonder if Dr. Tamara would agree to give you extra credit if you come up with a question. What do you think? Would that be a good idea? Yeah, so yeah, so we'll give you a few minutes to talk, and then we'll be back, okay?
Okay, just for the other professors in the room, what I do when we have lectures like this at Iona, if a student comes to the lecture and gives me a 2-page paper, that student gets extra credit from me. So students, okay, test your faculty members.
Yeah, good. So come up with some good question, okay? I'll be back in a couple minutes. I'm going to see. So who would like to ask the first question or say the first comment? Is somebody at that table? Yeah, come on. Good for you. There's a brave young man.
All right, so our question was, are you disappointed that you have to remotely operate the telescopes instead of visit Hawaii?
I do like going to Hawaii, so you could say I am disappointed. Now, but on the other hand, really, the focus of the thing is to use the telescope. And whether I'm in Hawaii or I'm doing it from my office or laboratory, we get the same results, basically. So it's part of the experience, you know. Have a long flight, 15 hours, you're on 2 or 3 different airplanes. You're living on this mountain. There's not that much oxygen there. It's hard to sleep at night. You're up all night, for one thing. But all things considered, I'd rather do it from Hawaii.
Good answer. Who's next? Good. Wonderful.
So my question is, how, as students here, could we view the infrared telescopes that you see remotely at Yale and in Hawaii?
How,
Would there be any way that we could see as a class the telescopes?
well, I guess the way to do it is to ask somebody who gets time on the telescope,
Such as you, right?
such as myself, to go through sessions with the class as we're taking data. I've done it with classes before at Iona. And so basically, I have this computer. I like to have two big screen monitors in front of me. But even in a laptop, we could access everything. We download the software. The software is common software. I forget the name of it. But once we get the password, well, we get the code, it would be our name, and the password, then we get right onto it. But you have to know somebody who gets time on those telescopes.
So a field trip, I can imagine it now, to Iona College or
Oh, yeah,
Yale.
come up to Iona.
That's right. That would be fun. So who else? Who else would like to ask a good question? We've had two very good ones so far.
Yeah. But anyway, as you're thinking of questions, to further answer your question, what I do with students, you've seen a couple students that I've worked with, I get them actively involved. When I, either at Iona or at the telescope, I start taking observations, and I have students sitting on either side of me. So one student writes down the log. I tell her how to write down the log. And then after about an hour, we switch places. So I put the student in the control seat, and I would watch over her shoulder to see what she's doing, help her out. Then after the other hour, we put the other student, and so on. So I think this is great. And in fact, the people at the telescope like to see our students because they know that when they go there, first of all, they're fresh faces. And they have been working with me already for, say, 2 years. And so they know what to do. And they enjoy seeing young people. And it inspires them also, I must say.
Yes, I understand that your field is astrobiology, and it looks like Mars does not have life currently, all the experiments they've done. But I understand there's a moon on Saturn that has the only ocean outside of Earth, an ocean of methane, and that there's a planet, a moon for Jupiter, Europa, that has maybe water underneath it, but may have energy from, Jupiter, the tides from Jupiter. So I guess my question is, what do you think in our solar system is our best bet for discovery of life?
Thank you.
Offhand, from what I know of the two moons, I would say one of the two moons would be. I mentioned earlier that one of the things that I would like to do is to find ozone on a planet going around another star, which would also put it into the category of being a possible location where life can exist. And the method that let me see if I could show you what would happen if we have ozone on another planet. Okay, if ozone exists on another planet, okay, we would still get these peaks. And as the planet is approaching us, the peaks would be shifted to the left. As the planet recedes from us, the peaks would be shifted to the right. And we know that these exoplanets move around their star. And people that study these things, they know what the speed is and so on. Now, I would say this is almost like an indirect way of doing it, because what happens is if we look at a direct way of doing it, there's too much starlight close to the planet that would block our view. But since this is in the infrared, and chances are the starlight is not going to affect it, we could isolate, these things from the light that's coming off of the star. Yeah. So that could be, if we're looking for planets that life can exist, we might say that we need the presence of ozone in the atmosphere of the planet to prevent ultraviolet light from going down to the surface of the planet. Because ultraviolet light and life does not exist too well. Okay. It would prevent the molecules from being formed that can support life.
Anyone else?
How do we know that Mars had a thicker atmosphere before, and what's the mechanism by which the atmosphere thinned?
Well, there have been a lot of different space probes over the last 30 years, well, since Viking, since the early 1970s. And they come up with scenarios for the history of the planet. Now, let me tell you one scenario. Mars has a smaller gravitational field than the Earth does, so that there are gases are leaving the Martian atmosphere at a higher rate than the Earth. Okay. Now, if you take that current rate and essentially work backwards, you find out that for Mars to have an atmosphere that it's only about 0.6% of the Earth's atmosphere. If we currently know the rate at which the atmosphere is disappearing, okay, there's a space probe going around Mars right now, MAVEN. That's one of the things that they're studying, what the gaseous atmospheric escape rate is. And you work backwards, and you find out that, say, 2-3 billion years ago, Mars had an atmosphere that was probably as thick as the atmosphere of the Earth. Now, from what we know of Mars and what we know of Venus, we're in between the two planets. About 95% of the Martian atmosphere and 95% of the atmosphere of Venus is carbon dioxide. Okay, so it's a rather different atmosphere than what the Earth is, but then tells us something about our own atmosphere. Probably 2 billion years ago, the Earth's atmosphere was mostly carbon dioxide. And we were able to get that change into oxygen, nitrogen, because of the presence of life. Yeah. So anyway, it's basically taking measurements today and simply working backwards with rate equations and so on.
That's good. One more question? Good. Over in this corner.
Great presentation. This really isn't a technical question, but I'd be interested to know what your thoughts are about the impact of the current administration on your work. I mean, obviously, it's highly costly, and we seem to have an administration currently that's cutting back on resources to EPA and venues like that. How do you perceive that playing out in what you're doing?
It could disappear very easily in a few years. Certainly, the telescope I use most of the time, well, the two telescopes I use are federally funded. I mean, it's the NASA Infrared Telescope. And, I think one of the views are, why is NASA getting involved in all these other things? If we don't get federal monies, I guess the next resource is going to be universities. Because as I showed you on Mauna Kea, some of the telescopes, you have the University of Hawaii, you have Caltech, you have Harvard. Okay, they're all sponsoring telescopes there. They're doing astronomical research. So, but even a lot of the university research is funded by federal government. Okay, my own PhD, I would say it's the federal government that paid for it. Because I got these grants, and my mentor got the grants, but it was for us to do work. Yeah. So I think it is a problem in the future. So that was the last question? Okay. Sister Duffy has the last question.
No, I'm just going to thank you for a very interesting talk. Yeah, thank you. So we know a lot more about spectroscopy now, right? And so thanks for coming, and thank you too for coming. I hope you've really enjoyed it. It was great, a night out, right? All right, so be careful going home, and come back again.
Watch out for the Martians.
The little green men.